So, hello everybody. It is 4 o'clock in the afternoon here, Central European Time, and I would like to welcome you to the second webinar introducing the new release 4.0 for all of you who want to use this standard to compare and to characterize cameras. We had already a first webinar yesterday. But let me just, for those who are here for the first time, quickly introduce myself. My name is Bernd Jene. I am the chair of the EMVA 1288 group and also senior professor at Heidelberg University. And so I can guarantee you will get firsthand information about the new and exciting features of release 4.0 for the EMVA 1288 standard. So let me share my screen with you. And today, I would like to introduce to you the basic parameters of the EMVA 1288 standard in this new release. You can see in the title that we obviously have two versions now in the new release, linear and general, and I'm sure you are curious to learn what this is about and what is really new here. I will start with a question: how can we relate the question of image quality, which we actually discussed and demonstrated in the first webinar yesterday? For those who missed this webinar, the recordings will also be available and you will get a link to it. You will also get, of course, the slides of the webinars so that you can also use this. So I will now basically go this decisive step from, well, something like image quality, which we discussed more quantitative, to really solid and good usable parameters. That will be the basic thing. In order to do so, it turns out it is useful to think about a camera as a kind of a model. And the EMVA 1288 model is surprisingly simple. And out of this basic model, you can immediately see what are the key parameters. And out of that, we can then, in the third step, look for the question, what do we actually have to measure? And I show you the most important things there. And finally, of course, there is always opportunity at the end to ask me some questions. So let's get started with image quality parameters. And what I show here on the first slide is basically a summary of what we learned yesterday. We have learned that there are basically three effects which make the quality of an image sensor not to look as good as you might expect. The first thing is that each time we take an image, we will get a slightly different value, and this is called the temporal noise. And of course, the higher the temporal noise is, the worse the quality of the camera is. Second thing is, we have not just one sensor. We have, of course, one camera, but within this camera, you have a lot, millions of pixels, individual sensor elements, and unfortunately, all these pixels are not the very same. They have slightly different responses. And that leads to another problem, spatial non-uniformity. And how can we describe now the spatial non-uniformity? Finally, the third thing is that unfortunately there is already a signal or an image even without light. And so the question is, how is this signal behaving and from which parameter does this depend? These are basically the three issues we have to deal with. That was a summary of the last webinar, and now in the next step, we, of course, could say, if we want to have an optimum image quality, we want to get all these effects as low as possible. There might be different choices because your application might be sensitive to one or more or less to one of these parameters. So the question can never be answered without an application in mind. That will actually be the topic of the next webinar tomorrow, where we specifically, not tomorrow, on Monday, sorry, where we specifically deal with the question, what do I need to know about my application to choose the best possible camera for it? Okay, so now let's go to the camera model and the key parameters. I mentioned already that the model actually is quite simple. It basically looks like that. The camera is simply treated as a black box. In other words, we make no assumption what kind of complicated processes are taking place there. The only thing is what we are interested in. We want to have a good image quality. That means we have to rate the quality of the output signal. And this is typically a digital gray value. It might have different channels for a color or multispectral sensor or polarization sensor. So you might have then different channels. And we look how large the signal is, but we look also how noisy it is. And here you find the two figures for it. One is μ, which is a channel of the camera, or also a derived parameter like degree of polarization, or like hue of color, or saturation of color. And the second parameter, sigma square of y, is then the variance in time. So from image to image, how quickly this is changing. And so we can measure, of course, simply the output of the camera. We take several images, measure mean values, and measure also then the variance or the standard deviation, so how the signal is varying from image to image. Then we know basically everything about the output. And then, of course, we have an input because we want to know how sensitive is the camera. That means given an input, which is something called an irradiance in physics, or exposure. And this is best expressed in number of photons hitting basically a pixel during the exposure time. So you, of course, from that you immediately know what we have to know about the camera is, of course, the exposure time. And we have to know, of course, also the pixel size. And then from, if we have calibrated our illumination source, we know then how many photons hit a pixel during the exposure time. Interestingly, I have put in here not only a mean value, that means a mean number of photons during the exposure time, but also variance. Obviously, we have already a noise source going into the camera. So even the input is not free of noise. This is something no camera manufacturer can avoid. This is simple physics. The interesting question is, within this black box, how many additional noise sources come in here? The essential thing, and this makes the usage of the standard so simple, that no internal measurements are required. We just measure an input-output relation. So we measure basically the mean number of photons. From physics, we know then immediately the variance, and we measure then the mean value and the standard deviation of the output signal. So you might think now, is this really sufficient? And actually, we did not start in the 1288 standard with this complete black box model. Until the last version of the standard, which was 3.1, we always had a linear camera model, so with some more information in the camera. But now the 4.0 extends to arbitrary cameras, also with nonlinear characteristic curves, so we can no longer make any specific assumptions within this black box. And we will see in a moment that this is not really a big obstacle. Let me go a step back and show you what the linear model was in 3.1. There we simply said, well, the photons are converted into charge units with an efficiency, which is called the quantum efficiency. Then you have additional noise sources within the camera and also dark signals. And you add up the photon-induced signal with this dark signal. Everything is amplified by a linear amplifier, quantized, and then you get the output. Then you can easily see that with this specific linear model, you have three unknowns: the unknown quantum efficiency, the unknown system gain, and the unknown variance of the dark noise. But please remember, you still measure only the output and the input. So, and these are just, so to speak, additional parameters which you really do not need for quality measurements of the camera. It's nice, of course, to know then the quantum efficiency, but the essential thing, of course, is how much noise do we have in the output signal, and how is this related to the input? That is really the essential thing, this thinking a camera as a system with an input-output relation. Okay, and then it immediately pops up what is the key parameter. The key parameter is simply how large is the signal compared to the disturbance, which for temporal noise is simply the signal to noise ratio. And I have written down the definition here for SNR, which is the mean signal induced by photons divided by the standard deviation of the temporal noise. And the mean signal, of course, only the photon-induced signal is of importance, and this is why we subtract from the mean output signal the mean dark signal, which we can easily measure by applying no radiation to the camera. So all these things can be measured, and also, of course, the standard deviation of the temporal noise can be measured. This is simply mean signal divided by standard deviation. And yesterday we also discussed a lot that our human visual system is not capable to measure actually SNR very well. We can only see noise if the SNR is smaller than 50 with a human eye. Everything what is larger seems to be noise-free, and we cannot measure it. And this is why it's so important to do really measurements and not just look with the eye onto the information. The SNR is, of course, measured as a function of the input, which are the mean number of photons which have been collected during the exposure time. And with a linear model, I go just back again to this slide where you have the parameters: quantum efficiency, dark noise, or temporal noise of the dark noise, a temporal variance of the dark noise, and the system gain. And interestingly, if you compute now out of these parameters, you can say, okay, of course, then you can get to this relation, and the system gain is no longer in there, which is not surprising, because noise and signal you are interested in are amplified by a linear amplifier in the very same way. So the gain just cancels out. It makes no sense to get a better image just to increase the system gain. The essential thing is how large is basically the standard deviation of the temporal noise compared to the mean signal. We cannot do, of course, this model curve if we have a nonlinear camera, but we can still measure, of course, since we can measure the mean and the standard deviation. Okay, now let's go what is about this second problem we have, that not each pixel has the same response and behavior. Well, we can do something like which I have named here. The name is not a common name, but it's nice actually to do it in this way. We have a signal to non-uniformity ratio. That means the mean signal divided by the standard deviation of the non-uniformity. So we look now for each value we get, how is this value now not changing in time, temporal noise, but from pixel to pixel. Then we can also measure a standard deviation. And to distinguish this, standard deviation from the temporal noise, we use a symbol S in the standard, whereas the correct symbol sigma is used for the standard deviation of the temporal noise. So you can immediately know, is this temporal noise a standard deviation of a temporal noise or of a non-uniformity? So you see exactly the very same thing. Next thing is we can add up these two things. The signal is disturbed both by temporal noise and by non-uniformity. So simply add these things up. The only thing you have to take care here, you are not allowed to add standard deviations. You have to add variances. That's a basic law of statistics. And so you see here that we add up the variance of the temporal noise, the variance of the non-uniformity, and of course then we have to take the square root out of this again to get the standard deviation again. So if we can even use this concept of signal versus disturbance, both for temporal noise and also for non-uniformities. Okay, so now let's go to the interesting question. Can we compare cameras to the best possible camera we can have? We can, of course, with this SNR, if we draw a graph of that, compare different cameras, and the camera which has a higher SNR is better. But the question then is still, how far is this camera actually away from the best possible? And unfortunately, the best possible SNR is not infinity, which means no standard deviation is 0. And the reason is simply, let me go back again, is that we have already a noisy input. So we cannot get rid of that noise. And so the question is very simple. If there are no additional noise sources inside our black box, that is the best what the camera manufacturer can do, then we have only the input noise. And if we have only the photo noise or shot noise, as it's called, what would then be the signal to noise ratio of our output signal? And the interesting thing is, for a linear system, we will get then simply the square root out of the number of photons we have collected during the exposure time, photons. So we still have to be very careful with one thing because we are not used to it. Normally we think almost ever about linear systems. So let me say a few additional words. The first thing is about these general things is that the EMVA 1288 standard release 4.0 has a change compared to 3.1, that it considers now only high frequency uniformities. That means more the frequency, the changes from pixel to pixel, and does not care about slowly changing non-uniformities, because these effects are anyway, I demonstrated that yesterday, more dominant by the lens, and by the way, of course, also by the illumination you use. The illumination is very hard to get very uniform. And this is why we finally decided we have to be more realistic to look what is really the contribution of the sensor, and it turned out it is only the high frequency part. So what we do is we take non-uniformity images by canceling the noise, by averaging, and then doing a high pass filtering, and then looking basically only for the changes basically from pixel to pixel. And this is actually what is disturbing. It's especially of importance, that's also a big step forward for release 4.0, that these non-uniformities are split into three different non-uniformities. You might have simply random variations from pixel to pixel. They look a little bit like noise, temporal noise. But you might have also very much disturbed row or column variation. That's what you see with vertical or horizontal stripes in the image. And that is, of course, very nasty, both for the human observer, but also for image processing algorithms which think there is an edge. for instance, in a row or a column. So that is not really what you want to have. And this is why we actually now describe the non-uniformities in Release 4.0 much more detailed in pixel, row, and column variations. For linear camera, we only speak about SNR. And the reason is simply we have a linear system, the input SNR, that means that actually the irradiance or exposure we want to measure is equal basically to the output SNR. With a nonlinear camera, we have to be very careful. Then the input SNR, that means the variance in the irradiance, is not equal to the output what we measure. What we are interested in, of course, is we really want to measure how good we can measure the irradiance and how much it is changing. So what we are really interested in and what is really essential is the input SNR and not the output SNR. But unfortunately, we measure the output or can only measure directly the output SNR. Fortunately, we've found a very easy method to compute the input SNR out of the output SNR in the version of the standard so that we can infer from the output SNR the input SNR. And that is essentially the important issue. For a linear camera, it's directly measured, but for a non-linear camera, we have to measure the input, compute the input SNR out of the output SNR, which is different. That is really important to keep in mind, and that we could do a simple calculation which goes basically via the slope of the characteristic curve was a big progress. So now we can go to the measurements. Let's start, we measure. What have we do to measure? We have to measure an input-output relation, and we measure the incoming photons. We measure the mean of the output signal, and we measure the standard deviation or variance of the output signal in tempo. And that means we get basically two pieces of information. One is a character called the characteristic curve, that is simply the mean output as a function of the mean input, and the mean input is a number of photons. And we basically do the measurements from complete dark, that means no photons at all, until, unfortunately, not until infinity, because each image sensor has a so-called saturation capacity, and that means we cannot go beyond a certain number of photons, but we have to cover the whole range from darkness to saturation. And that gives us a so-called characteristic curve. The second piece of information, which is only used directly in the linear model, is the function, the variance of the output signal as a function of the mean output signal. That's called the photon transfer curve. And according to the nature of the shot noise, of the photon input noise, that should be a linear curve, but this is no longer the case for a nonlinear camera. So this photon transfer curve is only used basically for the linear model, if you have really a linear camera. Okay, so let me just show you kind of a characteristic curve here for a linear camera. Here you have the irradiation in photons per pixel, which goes from about 0 to 10,000 here. And then you have the photo-induced Quay value. That means a Quay value minus a dark value. And you see a perfect linear relation here for this linear camera. The photon transfer curve in such a case is also quite nice linear. So the variance of the signal is a linear relation to the mean output signal. Okay, and then let's come to the non-uniformities. We have seen the whole temporal noise, which is really nasty, but it's easy to describe. Just one parameter, the standard deviation or the variance. But for the non-uniformity, it is much more difficult. We have, of course, also purely random variations like temporal noise, but we might have also low-frequency spatial drifts, which we do not consider much more because of the high-frequency part. But what is really nasty are periodic or patterned variations from pixel to pixel, or from row to row, or from column to column, or really the bad guys, the so-called outliers. These are single or clusters of pixels or sensor elements that show a very strong deviation outside of a statistical distributions. So You obviously see non-uniformities are not simply described by a single figure, and the standard has a lot of useful tools to distinguish all these different types of things, which I have no time, of course, to explain in detail here. So let me go to a very simple method which gives you a qualitative view in one simple graph. What we do there is we draw a row or column in the middle of the sensor that shows typically how the signal is varying from pixel to pixel or from within a row or within a column. Then we can also take the average or the mean of all rows. Imagine we have a row to a column to column variation. Then by averaging over all rows, we would not get rid of that. So the column variation would still be, you could still see in the mean row, whereas the pixel variations are basically cancelled out. Then we still cannot catch the outliers. Imagine you have 100 outliers in a megapixel sensor, then in one row you have a probability to catch, well, 10% probability to catch just a single outlier. But you want to see how many outliers are there and how large are they. So the simple trick is take a column, get the maximum value out of this column and the minimum value of this column and draw two other profiles. And this is called what we call the maximum value profile and the minimum value profile. And this show now basically all outliers. If in one column you have two outliers, you would catch, of course, the largest by that. Typically in a dark image, you would catch the hot pixels, so-called hot pixels, which have a much higher dark value. And if you're not in the dark, but in the standard typically takes 50% saturation, then you can show the negative outliers, the less sensitive pixels, or even the dead pixels which have really then zero value. Okay, let me just show you a horizontal profile in the dark, which is called the DSNU for dark signal non-uniformity profile. You see nicely pixel to pixel variations here. Otherwise, I think the signal is very flat, the dark, so very flat background, very nice. So dominant is really pixel to pixel variation. And if you average over all rows, which is a black row here, you see it's almost perfect. The only one thing you see towards the edge, it goes a little bit down. But remember, this is a 12-bit camera here, and it's less than 1 dN, the variation, so almost perfectly flat in the middle. However, if you look at the maximum, which are the orange curve here, now you see a lot of hot pixels. And you see that these pixels have typically higher values, and you would see them in an image as very fine, bright spots. You have not the same effect in the minimum. In the minimum, you would just go to about 3 sigma of the standard deviation here. So that means this is lower than here. Okay, if you do the same thing for the PRNU, you see again pixel to pixel variation, a very perfect sensor with a flat mean one, so no column and row variations, very nice smooth image. Of course, now you do not see any hot pixels, you have no super sensitive pixels, but you see in the blue curve here several pixels which have less sensitivity. So very nice, immediately at one glance you can see all these nice effects. Okay, now let me go to this essential parameter, back again the total SNR, because this, as I said, is the essential thing and you can get really almost everything out of a SNR plot. The SNR plot is done as a double logarithmic plot, and you will see always one line here which is the best possible image sensor, where you have no internal noise sources and also, of course, no non-uniformities. So that is the best possible thing that you can get. Here you see then all the measuring points, and then you see the real camera is a little bit lower SNR, but first it runs parallel, and then only in the very dark it gets steeper, and that comes from the dark noise. So the dark noise makes the camera only worse in basically at low irradiation levels. And the lowest what you can measure is where the SNR is 1. That means where the signal is as large as the noise. And here you can immediately see, okay, that happens for about 10 photons, a little bit more than 10 photons. My noise is as large as a signal. That is just what I can catch. There is, of course, a saturation threshold up here. And from the ratio of these both things, you immediately get what is called the dynamic range. So what is the smallest intensity and what is the largest intensity I can measure. And in addition, you see this dashed line. This is a total SNR. And then you can nicely see, okay, this camera behaves that the non-uniformities do not affect the quality at all at low irradiation, but at high irradiation, they do significantly drop the quality, because the SNR, the total SNR, including the non-uniformities, is significantly lower. Remember, this is a double logarithmic plot, so this is at least a factor of 2, a little bit more than a factor of 2 lower total SNR. That means that the non-uniformities are a little bit larger here than the temporal noise effect. So you can immediately get a feeling in which irradiation range you have which ratio of the influence of non-uniformities and temporal noise. The final thing we have to consider is a dark current. A dark signal is not constant. It increases linearly with the exposure time. And this dark current is expressed in electrons per pixels and per second. The practical relevance of this is that the dark current basically limits the maximum usable exposure time, because you can simply, if you have a large exposure time, saturate the sensor without any photons just by the dark current. The dark current, of course, if you do not get so far, increases, of course, the dark noise. And that is also of importance. The dark current is the only parameter which strongly increases with temperature. It doubles about every 7 to 10 degrees centigrade. And this is why this is one optional measurement in the 1288 standard to measure how the dark current behaves as a function of the temperature. All other parameters like the SNR, the essential SNR, is almost independent, only slight temperature variations, but this is a very strong temperature dependency. Just show you one example of a dark current measurement here, of course, for different colors. If they have the same gain, all these colored pixels, they should, of course, give exactly the same increase of the dark signal as a function of the exposure time and should be linear, as I explained it. And what you can also see, of course, that the dark noise is increased as well. That means if you take the same sensor with a higher exposure time, you get a higher dark noise, less dynamic range, and all these kind of things. That's always what you have to consider. So that finishes this quick overview of the basic parameters we have to consider. And what is next? We will have the next webinar in this series on Monday, next week, same time. And there is a typo. What you should know about your application to select the best camera for it. People often forget you not only need to know all the parameters for the camera, but you need also to know a lot about your application, because then you can only select which parameters are the most important ones. So that is what we will discuss on Monday next week. You can become a certified or you can be certified as an EMVA 1288X user. That is somebody who uses the data sheet and wants to select for application the best camera. This is more the knowledge required on the user level, and this is a knowledge we actually provide with these 4 half-hour seminars. On expert level, you really need to know all the details how to do the measurements, and this is much more demanding. And if you are interested in that, I have put the link in here. You can, of course, also download the standard documents and more general information on the link I have provided here as well. And so I hope that all this information was of interest to you. And I look very much forward to the third webinar, where we discuss now the question of camera parameters out of the perspective of an application. So which parameters are actually important for which application. Thank you very much for your attendance, and see you then again on Monday next week. Bye-bye and have a nice day.